In this video, I'm going to teach you about the work energy theorem, which states that the net work done on an object, or a system of objects, is equal to the change in kinetic energy. Now, I'd like for you to get out your College Board equation sheet. Go ahead and look at our formula for kinetic energy discussed in a previous video. And recall that anytime we're finding the change in a value or a quantity, we're going to take the final quantity and subtract from that the initial quantity. Therefore, the change in kinetic energy is equal to 1/2 mv squared final minus 1/2 mv squared initial. Now, in a previous lesson, I taught you a couple different ways to find net work. One of those ways was to find the net force. To take all of the forces, resolve them into components, and find the overall net force. That net force multiplied by the distance is equal to net work. Now, in the example with Stickman and the crate, that net force was parallel and in the same direction as the displacement, which means our cosine theta turned into the quantity of 1. Our cosine theta angle between the force vector and the displacement vector was 0. And of course, cosine of 0 is equal to 1. So we ended up with the following equation. Now, the question is, how do we go from this equation here to this here? Because that is what the work energy theorem is stating, that the net work equals the change in kinetic energy. Well, I'd like to show you how, and it's going to involve a series of substitutions. So considering Newton's second law, where the net force is equal to mass times acceleration, we can substitute mass times acceleration into our work equation. Once we do that, we see that net work is equal to mass times acceleration multiplied by the distance. Now the next step is going to involve a UAM equation. And please note we have no reference of time. For that reason, we're left with one UAM equation, and that would be that the final velocity squared is equal to the initial velocity squared plus 2 times acceleration x. Now, x is displacement. So we're going to go ahead and switch this over. You can see it in red now. We have a relationship between the work equation and the UAM equation, where we have acceleration times distance in the work, and we have 2 times acceleration times distance in the kinematics equation. So let's go ahead and make another substitution here. If we rearrange this and isolate 2 times the acceleration multiplied by the distance, on the left side of the equation, we set that equal to v final squared minus v initial squared. And you might see we're actually starting to get somewhere at this point. We're actually starting to make the work equation look like the change in kinetic energy. Now, if we take this and we divide both sides by 2, or distribute the 1/2 throughout, we get the following equation, which looks even more like the one we're trying to derive. The next step here would be to go ahead and substitute 1/2 vf squared minus 1/2 v naught squared into our work equation, because we're showing here that these two quantities are the same. So I'm going to take and remove acceleration distance from work and substitute in it these values here. Once we do that, we see that work net is equal to mass multiplied by the quantity 1/2 v final squared minus v naught squared. And now we simply distribute mass, and we end up with the change in kinetic energy. And this is what the work energy theorem is stating, that the net work, I cannot stress that enough, is equal to the change in kinetic energy. So let's go ahead and revisit a calculation we did in a previous video. And notice in the question here, I have 2 points that are highlighted and underlined from rest. And we are asked now to determine the final speed of the crate. So we know that our initial velocity, V naught, is equal to 0 meters per second because that's what at rest means. And we now know we're trying to find the final speed. Well, in this video, we did a number of calculations to find the net work equal to 183 joules. That's a positive 183 joules. Now, if we take the fact that the net work is equal to the change in kinetic energy, which I've provided a derivation and intuition for in this video, we can begin to substitute values. We can take our net work, which we found to be positive 183 joules, and set that equal to change in kinetic energy. But look what happens to our initial values here. They cancel out for the simple reason this object started at rest. Its initial velocity was 0. So that part of the equation goes away. Now we simply rearrange this equation, and I have multiplied both sides by 2 and divided both sides by 20 kilograms. And now we just need to take the square root, and we can solve for Stickman. Thank you. And we can solve for the velocity final of this crate and find it to be 4.3 meters per second. That is so cool. So in this video, I taught you about the work energy theorem. I showed you how it was derived, and we applied it in an example problem. And I'll see you guys in class.